So I'm going to basically talk about if we take IoE as connected intelligence, and intelligence is the stuff that Mark talked about, the processing, the data, the security. I'm going to focus mostly on the connected part. How do you provide connectivity to this many nodes? And the first question I'm going to talk about is something that Tom already touched upon, and that's the applications. So we know the usual suspects of applications in IoT. We have healthcare applications, we have home automation, industrial applications, automotive. But what I wanted to add here is perhaps the most exciting of applications, the ones that are most relevant, we still don't know. Precisely because we don't know the capabilities of the technology. The assumptions we make, the assumptions and the applications we think about today are based on the capabilities we have today. And we know technology evolves. We know that as technology evolves, the way we use technology evolves. And sometimes that evolution is very drastic, significant. The capabilities we have change over time, and the way we use technology changes. Now, have we seen this other places? Yes. Think about cell phones. 1970s, the most important application of cell phones was talking on the phone. It was a very important thing. You can talk on the go. But today, I don't know about you, but I don't really talk on my phone. Now, if my wife and friends were here, they would say, well, you never pick it up. But that's not true. I would defend myself saying that it's because I use it for email, for text, for other applications. But sometimes I use it for applications that you could never think about back then. Navigation. When I go to a new place, I turn my phone on, and that kind of gives me confidence. I know where I am. I'm going left and right. There's Uber. There's where I'm going around. So I think that part of those new applications we can never predict because we don't know all the capabilities of the technology as we are at this stage. Now we can go even further. Electricity. The killer app back then was, well, you have a light bulb. You can turn it on, and lighting is huge. Right? And I can imagine today you use electricity for more interesting ways also. But even if you take today's technology, if you assume that we are going on a trajectory that's predicted by today's technology, we see that Internet of Things is growing at an exponential rate. And the growth factor is higher than the other tablets and smartphones and PCs. And so we're getting into the trillion domain that actually Tom mentioned. So we're going to tens of billions, hundreds of billions, and now in trillions of connected devices. So that's the question I want to ask is, if we assume that we're going to the trillion connected devices, how do we provide connectivity? Assuming that we have good applications for that, how do you provide wireless connectivity for a trillion things? And to see the problem in that, let's take a look at the regular radio. So if you open up a radio, you do some surgery on the radio, you'll see that you have some usual suspects in there. You have the microchip with the packaging. You have some antennas. You have a reference crystal. You have some external components, some PCB board. You have some batteries on the reverse side. And my basically point is this kind of technology is not going to scale into the trillion numbers. Just because of, think about the batteries, think about the cost and the size and the scalability of the technology we have today. So if you're thinking about 1,000 radios per person, this Bluetooth low energy stuff is not going to get us there. This is my opinion. You may disagree. And the reason for that are three things. Cost is too expensive. So $10 trillion of these, $10 trillion, we would need a little bit more of banknotes from other places. Footprint is another issue. A lot of these things, you want to put them around. You don't want to have a credit card size radio around you. And the third one is scalability. 1,000 radios per person means at any moment in time, I want to talk to 1,000 things. Today's radio are not designed to do that. So what we really need is orders of magnitude improvement in all these three fronts. We can't just say, well, I have 10, 20% improvement here. I'll do some tweaking and optimization. I'll do some aggregation. No, it has to be orders of magnitude if we're getting to the trillion number. So let's see how we can get there. Now, one key observation you can make is today's radio, the way you design wireless devices today, is very symmetrical. So the sensor and my cell phone kind of have the same technology. In terms of complexity, it's very symmetrical. But if we move to this trillion number, it doesn't have to be symmetrical. I'm talking to 1,000 radios, so I can move all the complexity from that sensor all the way back to the main radio, and that gives me at least 1 degree of freedom to get order of magnitude improvement. So that's one key observation in our design. Now, in the next few slides, I'm going to pick one of the topics, one of the issues, and I'm going to, at the risk of oversimplifying, I'm going to spend a few slides describing the challenge and how we overcame that challenge. So I know Tom mentioned Tesla. So the first problem, you want to eliminate the battery. So eliminating the batteries is one key issue. We know we can't have 1,000 batteries. Tom mentioned this already. We have 1,000 batteries running, 1,000 devices running in a year each. So on average, every day I have to change 3 batteries at home. So that really doesn't make too much sense, at least to me. So wireless power delivery has been there. People have been playing with this for a long time. Now, granted, Tesla had much more cooler toys to play with than I'm allowed here. And safety probably wasn't the #1 concern back then. But he still had the main, I mean, the problem is still open today. The challenge is, how do you deliver wireless power to something that's very small? And that poses an extremely difficult engineering challenge. Something that's extremely small at a distance, at a reasonable distance. So what we really want is a distance to size ratio to be large. So if something is a millimeter sized and I want to communicate at the meter, I want the distance to size to be a factor of 1,000 or 10,000. So it's a very challenging problem. And I'm going to spend a couple of slides telling you why this is a challenging problem. Now, conventional wisdom, when we try to do wireless power delivery, we use our frequencies in which our cell phones operate 1 to 2 gigahertz. The wavelength is about 30 centimeters. And the device you want to power up is a millimeter. Now, the wavelength is much larger than the device. So what's the problem with that? The problem is you have, on the transmitter, you can't focus the beam into the receiver. That becomes much more inefficient on the transmitter side. And on the receiver, you can't pick up the power. The power coupling to that electromagnetic wave is much more inefficient. So what happens is you basically have a double hit here, and you can't power up effectively. So what you really need to do is make sure these two are matched. The wavelength and the size of the aperture are matched. And you can see this in a different way. Forgive me for a couple of equations here. So if you start and write the received power in Fries's equation at a given distance d, all you need from this equation is the wavelength ends up on the top here. So lower frequencies are better. And that's conventional wisdom, like lower frequencies travel further out. But the problem with this equation is it assumes a fixed antenna gain. Whereas in the IoT domain, we have a fixed radio size. I want to be a millimeter size. So we have to rewrite the equation. And when we rewrite based on a fixed aperture, you'll see that the wavelength ends up down there. And now higher frequencies are better up to a point that you get matched to the aperture. Now, what are the limitations on the other side? The limitation is that the power recovery efficiency, circuit microchip efficiency, goes down with frequency. So there's usually an optimal frequency that you have to find based on size and various different parameters. So once you have that, then you can actually go and have a more efficient power-up scheme. We can go into more details, take into account losses in the link. I don't want to go into the details of these equations, but the end story is with a given size, a millimeter size, the power that you receive goes up to a point that it saturates is where you get match to the aperture of the receiver. So it goes against the conventional wisdom because we're using very high frequencies into 20, 30 gigahertz to power up these tiny devices. So what we're proposing is you have this gateway device, as Tom mentioned. So you have this cell phone. And so this cell phone communicates with all these IoT devices. It could be a cell phone, your tablet. And these incoming messages that are in millimeter wave act as the downlink data as well as the power link. So not only you send the messages, but you also power up the devices using the same scheme. And once you power them up, they communicate back using another frequency in the millimeter wave. So that's the architecture we're thinking about and designing right now. So this was, of course, a crazy idea. If you go to a circuit designer and say, not only I want something that has no batteries, but I also want this tiny little thing, and I want it to operate in millimeter waves. They're going to come back and say, you're crazy. So we had to go and actually build this. So we built the whole chip, and you see here, this is the entire radio on a US penny compared to Mr. Lincoln here. And we're about twice the size of his nose. I mean, if you compare the dimension of this radio. And so this radio itself has, if we zoom into the chip, it weighs about a milligram, and it contains all the elements you see in a regular radio. It's a true single chip solutions. If there are any chip designers out there, one thing you notice about this chip is there are no pads. There are no electrical pads with this. Everything is wireless in and out. So when you want to measure this, it's very easy. We don't have some of the problems that Mark mentioned. You just go into the lab and wirelessly measure it. There's no landing and connection and all of that. So we solved that problem too. Yeah.
When you wirelessly powered it up, did it work initially?
I can't mention that on live TV. So the other problem is, so it includes everything, and it has wireless. Now, one thing I didn't talk about is energy is one point, but there's no timing in this clock, right? Every radio has a crystal reference that keeps the time. We don't have that here. So how do you design a radio with that? So we had to overcome a couple more problems, a few years of work condensed in one slide. It achieves 12 megabit per second on aggregate uplink, and the standby power consumption is of 1.5 microwatts. And this is orders of magnitude, as I said, lower than your regular radio. And in terms of cost, this would cost in the order of cents in the large volume scale, especially the testing would be easier. Large-scale testing would be easier because it's wireless. So here I have a video of this thing in action. So what we did is we got these radios, and we used double-sided tape, nothing fancy, double-sided tape, and we stuck them on top of a substrate. So you see these radios on top of this substrate, and the red trace is going to show the incoming messages to the radio, and the black trace here is going to show the uplink from the radio, the messages that the radio sends back. So let's see if the video loads up here. Here we go. So as you bring it into range, you'll see that this is the messages, the ultra-wideband messages that are coming back here. I don't know if you see it from the back. And then we also tested from the back side. So if you look at the back side, you'll see that, again, I get the messages in, and I respond with the coded data. We're doing a PPM coding on the return. So, with this technology, now you can think about applications in which you can have trillions of devices. For one application, very short-term applications, we were thinking about is if you have a temperature sensor on this, and you put it on a Band-Aid, now you have a whole device that costs a few cents. And everyone everywhere that goes to a medical facility, whether a hospital or a clinic, will have one of these Band-Aids, cost a few cents, and they can monitor their temperature wirelessly. So you can put a lot of this radio on a lot of different applications, and because of the cost and size, you have a lot more flexibility. So let me go to a different topic now. I'm going to spend a couple of slides on another technology we've been working on the past few years. And the question we asked ourselves here is, can we take this one step further? Can we make it smaller, going to the dimensions of a human hair, and embed them in the human body as implantable devices? Now, one thing you might ask is, why the hell would I want one of these in my body? Well, there are some applications, believe it or not. For the classical ones are the pacemaker. But there are applications where you implant them in the brain for modulating neural activity. You can think about applications where you actually implant this close to an organ to monitor and modulate local physiology. You can think of them extremely going into the bloodstream, measuring biomarkers in the extreme sense, or a digestible pill that we just saw in the previous slides that actually goes in and then communicates. So the key challenge here is, although we want all of this implantable devices, we also want these to be extremely small but keep the functionality. We don't want them to be small and dumb. We want them to keep the essential functionality of a radio and a sensor, but at the same time, the dimensions need to be small. Now, the problems are kind of the same, except for, so you need to match the wavelength to the aperture, except for two things. Now we want them to be smaller, so we're going to less than a millimeter size. And the second problem is the human body is a big obstacle, and it's not easy to power up in something inside the human body. So that's two problems we have. So the usual trick we played on the other technology, we can't play here. If we up the frequency to reduce the wavelength, the absorption increases. So think of you have a microwave oven, right? 2.4 gigahertz, a lot of that energy translates to heat, not in going into the device. So the question we asked was, do we know of any other waves that are safe in the human body, and at the same time, the wavelength is much smaller? And the answer to that is yes. We know of sound waves, same technology used for ultrasound imaging. The speed of sound is 5 orders of magnitude smaller than the speed of light, so that therefore the wavelength is much smaller. So now I can effectively power up these implantable devices at extremely small dimensions. And at the same time, the transmitter can also focus the energy because of the small wavelength into the receiver. So that's the technology we've been thinking about. And just to show that this is not just totally a pipe dream, we actually went ahead and designed the system with a bunch of transceivers. So this would be very similar to your ultrasound imager. It will send messages to these implantable devices and also communicate back. And we built the first generation. This is a project in collaboration with Professor Kuryakub at EE department. So the first generation, we had the proof of concept device, which has a piezoelectric device, harvests the ultrasound energy, translates it into electrical energy, and then the chip takes that energy, communicates on downlink, and communicates back. So we have bidirectional communication with these embedded devices. And as you can see, the second generation, we're already pushing the dimension of these things further down. Again, on a US penny, now we've graduated from Mr. Lincoln's nose to Mr. Lincoln's eyes, I think here, making them even smaller. So we're pushing down to about a couple of 100 microns dimension. So what I wanted to conclude with is, first of all, the most interesting applications that we can think about, the most exciting of applications are yet to come. So we still have a lot more exciting technology to work with. And as we have more evolving technology, we'll have better, more exciting applications. And secondly, looking at the horizon of IoT, there are a lot more degrees of freedom in terms of the ways we can interact with these new devices. So with that, I want to go to acknowledgements, acknowledge the collaborators and students, and also the funding agencies. Thank you.